In this video, we'll take a look at how we will extend a partial byte representation to take it out to a full byte. So let's start off with a number less than 8 bytes, correction, less than 8 bits. And we want to get this to a byte. So we have two options. We can put more numbers on the left, or we can put more numbers on the right. So let's look at the left first. If we go this way, let's recopy our number down and think back to when we put a table and we track our positions for our numbers for when we want to expand this. Now we're going to need 3 more positions because there's 5 numbers. And we always start off at 0, so we have 0, 1, 2, etc. all the way up to not 8, it'll be 7 because we started at 0. So now we have to decide, this is a binary system, so should we put 1s or 0s in here? Well, if we put a 0, it's not going to change the number. So for example, here we'll put a 0, and that would just be 0 times 2 to the 5, which will be 0. But if we wanted to put a 1 in there, we'd have to say 1 times 2 to the 6, which it doesn't matter what this number is. We can see 8, 16, 32, 64. The point is, it would change what our underlying number is. So we can't use 1s, we have to use 0s. So this means in order to what we call left pad the number, we have to add just 0s onto the side of it. So now if we want to expand this out, our binary number is going to be 0, 0, 0, 1, 0, 1. And if we write the expansion, we have 2 to the 4, and then we'll have 2, 1, and 0. So that's going to give us 16 plus 4 plus 2 plus 1. If you add those together, you'll get 23. And this is what we'll get if we add them onto the left-hand side. Well, let's explore what happens if we go to the right-hand side. Here, we'll create our table again. And I'll write my numbers first just to save a little bit of space, make the table a little bit cleaner. Now when we go to fill in what our numbers are going to be, because we're right padding in this case, we're putting 0s on the right hand side, we'll start by copying down the first number into our top number, or the most significant bit for our representation. And again, the same argument would apply. We want to put 0s here instead of 1s, because if we put 1s, we can see already that we would change the number. So this would give us a binary number of this. Now, the problem that we'll run into is when we go to expand this one, we'll have 1 times 2 to the 7 plus 1 times 2 to the 5. We skipped 6 because there was a 0 there. Plus 1 times 2 to the 4. 1 times 2 to the 3. And that will give us, these numbers are a little bit uglier, 128 plus, the next would be 64 for 2 to the 6, so this is 32. And then we have 16 plus 8. Remember the trick, if you look at the ones place, groups of 10, so 120 and 2 is 130. 130 plus 30 is 160. 176 plus 8, 6 and 8 will be 14, so 184. Obviously, these two numbers are quite a bit different. Well, why? If we look at the position numbers, here our ones place, or what we treated as our ones place initially, was moved up. So instead of being 2 to the 0, being 1, our lowest part of the number was 2 to the 3 would be 8. So then we effectively scaled our number up. Which, if you say, well, what's 23 times 8? Then 3 times 8, is 24. We carry our 2. 2 times 8 is 16. So we get the same number because of how we did this shifting over here. Incidentally, that's how multiplication works in a computer. They often do shifting like that. So the takeaway from this is if we want to get a full byte representation for a partial representation, we have to do our left padding approach here. If we try to do the right padding, we're going to change what our underlying number is going to be. So just make sure you do a left padding approach. That ends the video.